Generalizing the uncertainty principle. As you saw last question, we have the new bracket algebra known as commutators, and we could generalize the uncertainty principle using that. Here we wish to prove the famous, quote, your name uncertainty principle relating uncertainty in position, A, the observable A equal X, to the uncertainty in energy, the observable B equal P squared over 2M plus V. And we want to show that if those are the two observables, that we have sigma X, sigma H is greater than H bar over 2M, magnitude of the expectation value of P. And for stationary states, this doesn't tell you much. Why not? So to start this off, let's go ahead and define the generalized uncertainty principle. Here we have sigma A, sigma B, both squared, are greater than or equal to 1 over 2i expectation, the curl brackets, of the commutator of the operators A and B respectively. And of course squared. Eventually we'll take the square root, no big deal. Here we're given A and B in the question statement, so we need to focus on the commutator bracket before we can simplify anything else in the expression down. Here we see that the operators are the position and the Hamiltonian, or the energy. So when we plug these in, we see that the position operator is just the variable x, and we have the Hamiltonian, which is composed of momentum squared and the potential. Here, thanks to a property known as linearity, we can, separate them with the plus sign. Again, we showed this property last time, but just as a refresher, here's the property of linearity for the commutator brackets when we have the linear combination on the right-hand side of the bracket instead of the left-hand side. Still, kind of feels normal at this point now to see it written out like this, no big deal. But, in the process of simplifying this, of course, this is a constant, take it outside. We have to deal with this p squared term, which goes to p and p, so we have to see here that we have a product there, and that's what is going to be needing to be handled. We also saw last time that we had the distributive property, but that was for something in the left-hand side of the bracket. So we call that the left distributive property. What about when it's on the right-hand side? Well, there's our right-hand distributive property. Okay? If that's the case, then you see we simplify down to this form where BC is the product on the right-hand side, and C goes to the left bracket, and B goes to the right bracket. Weird kind of inflexive symmetry there, but nonetheless, I think we can now see we have to use this in order to simplify. So plugging in the form, you see that we just have the, P on the left-hand bracket to the right, and P on the right-hand bracket to the left. Okay, no big deal. And then we see that we just expand the V bracket, the X and V bracket, which we know was going to equal 0 anyways, due to the fact that they were constant in this case, or rather that they're variables, so they commute. No big deal there. Get rid of them. If you need, the form of it, you see that here. The constants will always go to 0. No big deal. But what we do notice on as far as the position and momentum is that this operating bracket or commutator bracket is equal to h bar times I, as you see in the orange, and both of them have that, so you factor that out here, and that's a wonderful thing. Clearly that goes to 0 when we switch the variable placements, same as what we did in the property. Really, same thing here. But for the momentum thing, we have 2 of them, so cancel the factors of 2, and then you're left with the I h bar over m p. Cool, cool, cool. Really not that hard of a problem, just really cumbersome if you're not familiar with the commutator properties. So go ahead and plug that in here. You see that we're finding the expectation value. All this is a constant. Remember the inner product, so you can take them out. So we do that, and we're left with I h bar over m, where the i's cancel. And if you read the book, you saw that they purposely put the I in there for this reason. And the broader sense of the canonical operators is the fact that The I has to be there because the canonical operators are defined as Fourier transforms or canonical conjugates of one another. So it's pretty darn clever, I have to admit. And I'm really interested to see how this transponds as we get deeper into theory. So let's move on to the next part and finish simplifying. So once we finish simplifying that out, we see that we have a square on the left-hand side. We can put the bases together, which is what we do with the sigmas, and then we can cancel the squares. It's not just a straight cancel. We know that we're going to have a magnitude here, because if we take the square root of the right-hand side and the left-hand side, positive of course, we get an absolute value here, but since h bar 2m are positive values, we're good there. But to guarantee that the expectation is positive, we keep the magnitude there, and thus we prove what we were aiming to prove. So again, not too bad, just a little bit of work with the definitions. And then, we were asked about specific things like the stationary states. I mean, look, the stationary states being eigenvalues and, what we saw in chapter 2 shows that the standard deviation in the value is 0. The expectations are going to be equal to one another, so we're fine there. And then on the right-hand side, if they're stationary states, we saw that the derivative of the position expectation went to 0 with the Ehrenfest theorem. So we saw or that the momentum expectation value was 0 due to odd integrals. Either way, you get 0 there. So you have the inequality that reads 0 is greater than or equal to 0, which just is not insightful. It's not exactly anything useful for us. So kind of lame there, but again, quick problem, easy problem. I probably overcomplicated it for the sake of making sure every detail was in this one, but definitely better to check yourself. Again, make those commutator list, and we'll see you at the next one. Thanks for watching, and until next time, stay curious and happy learning.